Welcome friends. In this module, we are going to discuss software engineering methodologies. The objectives of this module are to be familiar with the life cycle models used in software engineering, to get an idea about implementing modularity to a software, to study about the various factors related to modules, to understand the different tools and techniques used for the software development, to have a knowledge about the software ownership and liability. Earlier, a strict sequence of development phases was followed in software engineering, such as analysis, design, implementation and testing. Hence, the analysis of system should be completed before the design begins, the design should be completed before implementation, etc. The development process was allowed to follow in only one direction and referred to as waterfall model. But now the scenario has changed to contradict the structured environment of waterfall model, and the trial and error process is proved to be vital to creative problem solving. This fact leads to the incremental model for software development. In this model, the desired software is constructed in increments, such as the first is simplified version of the final product with limited functionality. This version is then tested and evaluated by the future user. More features and functionalities are added and tested in an incremental manner until the system is completed. The software development models. A life cycle model is a graphical representation of different phases of a life cycle accompanied with a textual description of their ordering. Different life cycle models present the basic activities in different ways. The advantage of using a life cycle model is that it allows the development of software in a systematic and disciplined manner. If only a single programmer is involved in the development, he can decide the steps by which he will develop the system. But when the development of a software product includes a team of programmers, there should be an understanding among the team members as what to do, when and how. Hence, the use of a suitable life cycle model is essential to the successful completion of a project. The classical waterfall model is the most obvious way to develop software, but it is not a practical model. The incomplete versions of the final product, called prototypes, are built and evaluated in the incremental model. In this model, these prototypes are evolved into complete final products by adding additional features, and this approach is called evolutionary prototyping. In some cases, the prototypes may be discarded and a fresh implementation is done for the final product. This approach is known as throw-away prototyping. Rapid prototyping is a type of throw-away prototyping in which the proposed system is constructed quickly in the early stages of development. This prototype would consist of only a few screen images to indicate the interaction of system with the user and the capabilities of the proposed system. These rapid prototypes can be used as a demonstration tool and has the advantage of clarifying the system requirements during the analysis phase or as tools during communication between the parties involved. Another evolutionary prototyping used is known as open source development. This is the way today's free softwares are developed. The open source development of a software package is as follows. A single author writes the initial version of the software and posts this source code with documentation on the internet. Then it can be downloaded and used by others free of cost. The users who have downloaded the source code can modify or enhance the software or correct the errors they find. They report these changes to the original author. Then the author incorporates these changes and an extended version will be posted for future modifications. In this way, a software package will be evolved through several extensions in a small amount of time. The important shift from waterfall model is the methodology called extreme programming or XP. In the XP model, software is developed by a small team of individuals, likely 10 or so, working in a communal workspace where they freely share ideas and assist each other in the development project. The software is developed incrementally by repeated daily cycles of analyzing, designing, implementing and testing. Thus, the software packages appear on a regular basis, each of which can be evaluated by clients and point toward further increments. Extreme programming is characterized by flexibility. The comparisons of waterfall model with XP reveal the breadth of methodologies that are being applied to the software development process. Modularity. The division of the software into smaller manageable units lead to modularity, and these smaller divisions are called modules. Each of these modules deals with only a part of the software's overall functioning and acts as an abstract tool for the other modules in the system. A modular design implies that a problem has been decomposed into a set of modules. Modular implementation. Software modules come in different forms. In an imperative paradigm, modules are procedures. In an object-oriented paradigm, objects are modules. Modularity refers to the functional independence of program components. This approach facilitates the divide and conquer principle by decomposing a problem into smaller manageable modules. Modularity is an important characteristic of a good design solution. By examining the structure of a module, it is possible to assess the modularity of that design. In the following figures, two distinct design solutions to a problem are given. The modules are represented as rectangles and labeled M1, M2, etc. The invocation of a module by another module has been shown as an arrow. The diagrams which used to represent modules in this fashion are known as structure charts. The design solution of figure A is simpler than that of figure B since the interactions are low. But there are no quantitative metrics to directly measure the modularity of a design, and so it is not possible to say which design solution is more modular. However, the modularity of a design is characterized by the cohesion and coupling in the design. A design solution is said to be highly modular if the different modules in the solution have high cohesion and their inter-module couplings are low. A software design with high cohesion and low coupling among modules is the effective problem decomposition, which leads to increased productivity and decreased complexity. Coupling. Coupling between two modules is a measure of the degree of interaction or interdependence between the two modules. Two modules are said to be highly coupled if either of the following two situations arise. First, if the function calls between two modules involve passing large chunks of shared data. The other, if the interactions occur through some shared data. If two modules do not interact with each other, or if they interact by passing no data or only a few data items, they are said to have low coupling. The degree of coupling between two modules depends on their interface complexity. The interface complexity is determined by the number and complexity of parameters interchanged when one module invokes the functions of the other modules. The different types of coupling that exist between two modules are data coupling, that is, two modules are data coupled if they communicate using elementary data items, for example, integer, float, character, etc. Stamp coupling. Two modules are stamp coupled if they communicate using a composite data item such as structure in C. Control coupling. If data from one module is used to direct the order of instruction execution in another module, then the modules are said to have control coupling. For example, a flag set in one module is tested in another module. Common coupling. Two modules are having common coupling if they share some global data items. Content coupling. Two modules have content coupling if they share code. If the jump from one module is into the code of another module, content coupling occurs. Modern high-level languages do not support such jumps across modules. The different types of coupling are shown schematically in the following figure. Cohesion. Cohesion is a measure of the functional strength of a module. When the functions of the module cooperate with each other for performing a single objective, then the module has good cohesion. If the function of the module do different tasks and do not cooperate with each other to do a single piece of work, the module has a poor cohesion. The degree to which the different functions of the module cooperate to work towards a single objective is the cohesiveness of a module. The different modules of a design can possess different degrees of freedom. The different types of cohesion are depicted below. Cohesiveness increases from coincidental to functional. Coincidental cohesion. A module is said to have coincidental cohesion if it performs a set of tasks that relate to each other very loosely. For example, consider the given module in which the functions of the module carry out different and unrelated activities like student enroll, book issue, request teacher leave, request assistant leave, etc. That is module random operations, student enroll, book issue, request teacher leave, request assistant leave. Logical cohesion. If a module is said to be logically cohesive, if all the elements of the module perform similar operations such as error handling, data input, data output, etc. For example, if a module contains a set of print functions to print various types of reports such as grade sheet, salary slip, annual report, etc. Temporal cohesion. If a module contains functions that are executed in the same time span, then the module is said to possess temporal cohesion. For example, when a computer is booted, several functions need to be performed. When a single module performs all these tasks, then the module can be said to exhibit temporal cohesion. Procedural cohesion. A module is said to possess procedural cohesion if the set of functions may work towards entirely different purposes and operate on very different data. For example, the functions login, order, print, update and logout all do different things and operate on different data, but they are executed one after the other. Communicational cohesion. A module is said to have communicational cohesion if all functions of the module refer to the same data structure. For example, the functions administration, marks, grade sheets, etc. access and manipulate data stored in an array named student data defined within the module. Sequential cohesion. A module is said to possess sequential cohesion if the different functions of the module execute in a sequence and the output from one function is input to the next in the sequence. Functional cohesion. A module is said to possess functional cohesion if different functions of the module cooperate to complete a single task. For example, a module containing all the functions required to manage student details show functional cohesion. Here, student enroll, student marks, compute grade, compute attendance, etc. work together to generate the student reports. That is, module student report consists of student enroll, student marks, compute grade and compute attendance. According to the words used in describing the works of the module, the type of cohesion can be identified. Components. The modular approach to software development offers prefabricated off-the-shelf components to develop large software as with other streams of engineering. In object-oriented paradigm, the objects form complete self-contained units that have clearly defined interfaces with their environments. Once the object is designed, it can be used anywhere where the service of the object is required. Research in the development and use of components has led to the field of component architecture, in which the traditional role of a programmer is replaced by a component assembler who can construct software systems from prefabricated components. In many of the graphical development environments, these components are displayed as icons. To obtain the desired functionality, the component assembler needs to select the suitable components and connect them with minimal customization. These components can be extended to be suitable for particular applications without any internal modification. Sun Microsystems and Microsoft are best suppliers of these types of components. Components of Sun are called Java Beans, and Microsoft's approaches packaged in the software development environment called .NET. Tools and techniques. Some of the modeling techniques and notational systems used in the imperative paradigm are the important ones of the software engineering discipline. In the imperative paradigm, software are built in terms of procedure. Some of these are useful even in the context of object-oriented paradigm. Even though procedures are the building blocks of software, a procedure can be identified only if the data to be manipulated are considered. A data flow diagram is a means of representing the information gained from data flow analysis, in which by studying the movement of data through the system, the locations at which data processing occurs are identified. In a data flow diagram, arrows represent data paths, ovals represent point at which data manipulation occurs, and rectangles represent data sources and stores. For example, the following data flow diagram represents a student registration process. These data flow diagrams are used to understand the proposed system during analysis stage. Another tool used in both analysis and design is the entity relationship diagram or ER diagram. It is a pictorial representation of the items of information called entities within the system and relationship between these entities. Entities are represented as rectangles, relationships are represented by diamonds and are connected using arrows. There are different types of relationships between entities such as one-to-many, one-to-one and many-to-many. Yet another tool used by software engineers is the data dictionary. It consists of metadata or information about the data items that appearing throughout a software system. It improves the communication between the future user and the software engineer that help to convert the user's needs into requirements and specification. It helps to establish uniformity throughout the system. Unified Modeling Language. UML is a collection of modern tools to incorporate with the object-oriented paradigm. One of these tools is the use case diagram that depicts the proposed system as a large rectangle in which the task performed by the system called use cases are represented as ovals and users or actors of the system are represented as stick figures. For example, a part of the administrator system is shown in the following figure. Use case diagram gives a view of the proposed system from outside whereas another UML tool called class diagram represents the structure of the classes and relationships between classes. It is similar to entity relationship diagram. ER diagram represents relationships between entities, which is less precise. Class diagram represents static features of a program's design. To express the dynamic features such as sequence of events, UML provides collaboration diagrams. Class responsibility collaboration or CRC cards are useful in validating object-oriented design even though it is not a part of UML. The description of object is written on this card. Design patterns. Another tool used by the software engineers is design pattern. It is a pre-developed method for solving recurring problems in design. For example, the adapter pattern is used to solve the problems in constructing software from prefabricated modules. A decorator pattern provides a means of designing a system that performs different combinations of the same activities depending on the situation. The identification of recurring problems and the creation of design patterns for solving them are the ongoing process in software engineering. Good design principles such as minimizing coupling and maximizing cohesion are important in the development of high quality design patterns. Documentation. A software system should provide adequate documentation which helps the users to learn, use and maintain the system. Software documentation hence provides three services, which are the three categories of documentation, with user documentation, system documentation and technical documentation. The user documentation explains the features of the software and usage of the software. It is designed for the user and written in application terminology. The system documentation is interested for the software maintenance. It describes the software's internal composition. It consists of the source version of all the programs in the software. It also consists of a record of the design documents describing the system specifications and the way how these are obtained. The purpose of technical documentation is to describe the method of installation and service of the software system. The technical documentation does not deal with the design and usage of the system. Instead, contains the details of how the components of the system can be serviced. The technical documentation is used by a system administrator who is responsible for servicing the software. Software ownership and liability. The copyright and patent laws are well established, but the characteristics of software confuses the application of these to the ownership of software. Copyright laws were established to protect an author's right to literary works. Here, the value of the product is in the expression of ideas and not the ideas themselves. But the value of software is generally in its function rather than its form, where the copyright laws protect the form rather than the function. So, a direct application of copyright laws is not possible on software products. Hence, courts have applied techniques called filtering to separate similarities. The filtering is to identify the properties that do not imply violation of laws, remove those properties and then base the judgment of violation on what is left. In effect, the look and feel of a software package has many of the characteristics of the properties protected by copyright laws. Patent also has the fundamental problems when used to protect software ownership rights, but it is expensive and time consuming process to obtain a patent. However, a copyright and patent laws are designed to protect the rights of creators and inventors so that their achievements can be known to the public. Often, a piece of hardware or software will come with a license agreement that states the creator company X is not liable for any damages that may result from the use of their product. But the defenses against liability often claim to apply careful software engineering principles during the development. In this module, a brief description about the techniques and methodologies used in the development of software systems is discussed. This module provides a very brief idea about the various prototyping models. Here, modularity is discussed in detail with the various features such as cohesion and coupling. It also goes through the modeling tools such as ER diagram, DFD and UML. The module ends with a reference to the importance of documentation and software ownership and liability. Please try to answer the following questions. Differentiate between traditional waterfall model and newer prototyping paradigm. What is evolutionary prototyping? What is meant by coupling and explain the different types of coupling? Explain the different types of cohesion. What are the traditional modeling tools used in software engineering? What is the importance of documentation in the realm of software engineering? Briefly explain the issues related to software ownership and liability. Hope you enjoyed this session. See you next time. Until then, bye.